All right. Any problems? So everybody's logged in. Okay, excellent. So the lab we're doing now is this one called Lab 2 VNF in-band telemetry. So open the document so that you can follow along, because there's going to be code snippets in here that you can cut and paste from and avoid a lot of typing. So get that open. The other tool we're going to need is the Programmer Studio IDE that we've been describing to you previously. So I'm going to open that up. DXDD. Right. I just want to go back to this slide now for a brief moment, and if everybody can just pay attention to what's happening here. So what you've done is you've remote desktoped into a Windows virtual machine running somewhere in the cloud. That's this card that you've been given. If you haven't been given one of these yet, put your hand up. This is a different card. This card represents a piece of physical hardware that you're going to load software on. So there's a hand here.
Oh, no, sorry. I thought you meant one of those cards.
This card represents that card. So, well, you can get one of those at Open-NFP.org. As Bapi said, it's cheaper than an iPhone. So, all right. So we're going to use these details later to connect to one of these cards and deploy software on the card. So this card is installed in a real physical server somewhere. Yes?
You want to back away from the microphone.
Oh, sure. Am I too loud?
Well, you're just too close.
Where do you want it?
Maybe just back up.
Like that. Is that good?
Yeah.
All right. So these cards we've deployed in real servers. And the setup has got actually two cards in. There's a Netronome smart NIC, and then there's a regular NIC that is connected to it with a piece of fiber. So the idea is we can play traffic in and out of the regular NIC and see it coming in the NIC port of the smart NIC. And that's what this card is. So when we get to it, we're going to connect to it with this. All right, so let's start at the beginning. Let's create a new project. So for that, you navigate in the IDE to File, New Project. Not File New Project. And we give it a name. So I'm just going to call mine Lab 2. And then we need to select a hardware variant that we're going to deploy onto. Now, the cards that we've installed in those physical servers for you is this variant, NFP 4XXX-B0. So what this is doing is defining some of the configuration of the card, like what ports are connected to the MAC of the thing, how much memory is available, all these kind of things. So if you select the wrong thing here, you're going to get troubles later. So please get this right. Also important is to check this P4 box. We're developing a P4 application, and by doing this, we enable the IDE to enable all sorts of P4 stuff that we need later. And we're going to be implementing this version of P4. It's just an option for the compiler. And now, instead of starting from scratch with a new file, we're going to insert the source file we downloaded earlier. So those things that we extracted, we're going to go to Project, and we're going to say insert a P4 source file into the project. So I saved mine in Downloads, Labs, DXDD. This is P4 Lab VNF int. And if If you want to really cheat and go to the end, you can load the complete one. Don't do that. I'd like you guys to start with P4 Labs skeleton. So this is just a starting point for us to work from. Yeah, P4 Labs skeleton. Now, once you've imported that into your project, inside this file view on the right-hand side, you can expand the window as needed. Mine was a little bit squashed on the side here. Under P4 Manage C, you should find your skeleton file that you've just included into the project. You can open it up. Right, if you want to work a little bit ahead of me now, now's a good time. I'm going to take a little bit of time to explain the source code. Not a lot of time, but just to briefly kind of familiarize yourselves with what is in here. So if you know P4, this should start to look familiar already. We define some packet headers to match Ethernet, so source and dest MAC addresses, and an Ethernet type. And then if it's IPv4, we're going to also go as far as matching an IPv4 protocol header, and that looks like this if you know anything about IP. I'm not here to teach IP today, I'm here to teach P4. And we're going to go even one level deeper. We're going to go and look at what does a TCP header inside an IP packet look like. And that is characterized by various things such as the source and dest port and sequence numbers and acknowledgements and windows and all these fun things that go along with TCP. Then you'll see we define some additional metadata. Now the reason we're doing this is we're going to calculate TCP checksums. And if you know anything about TCP checksums, a TCP checksum is calculated on components of the IP header combined with the rest of the data in the packet, in the TCP packet. So we're going to and amongst that, one of them is the TCP length, which is slightly different from what value is actually stored in the TCP header. So we're going to use this metadata to perform a calculation in P4 of what that field in the new header should be. Then we instantiate these various headers and metadata that we've defined, and we define the field list that applies to this, both the IPv4 checksum and the TCP checksum. And here you see we're going to reference this new metadata that we defined here. So this is the layout of the TCP pseudo header that we use for calculating checksums along with the payload of the packet. Okay. And then we define the TCP checksum as calculated over this field list that we've defined. And we tell it that this is the algorithm that's appropriate for TCP checksums, and the output is 16 bits. And we instruct the P4 compiler to generate code to verify the checksums on ingress. So if we receive the valid IPv4 packet, we're going to also go and verify the TCP checksum. So if valid is saying that if the IPv4 checksum was valid, then go and verify the TCP checksum as well. And then on egress, we are also going to do the inverse. We're going to, if we've made changes to the packet, we're going to recalculate the checksum and write it back. Okay. In terms of parsing these headers, that's fairly straightforward. That's like a fairly common P4 parse graph. So we're going to extract the header, and then based on what we found in the header, we're going to either decide that it was an IPv4 packet and parse further. Otherwise, we're done. We're only going to extract up to L2 in that case. And the same for IPv4. If it happens to be a TCP packet, we're going to dig a bit deeper. And if it's not a TCP packet, we're just going to stop it at L3. Okay, so I'm going to... yeah. Okay. So I haven't been doing anything making progress yet. So has everybody managed to at least import the file into the project so far? Is anybody still stuck with that? So let's not move the mic after that. Okay. So we're building a NIC here, so we need to forward things. So we need an action to do that. And that's going to just modify the standard metadata field called egress spec, which, if you've read the P4 specification, is going to define what port this packet leaves on. So when we pass in that field, we're going to go out this port. And then we have a forwarding table that looks up based on the ingress port. Oh, I can also do that, sure, let's do that. Where do I do that? Tools, font and color. Right, that's a good idea. I want to go this one. Okay, and then 15 is good. What should I make it? 12? 13. Okay. Does that look good? I can go a little bit bigger. It's not a problem. Let's go 15. Doesn't go bigger. Yeah. Okay, so that's as good as it gets, guys. Sorry. Right, so we're defining a table that's going to match on the ingress port, and then the action in that table is going to get some host configured, control plane configured data to tell it, given an ingress port, what egress port are we going to go out. So it's a very, very simple forwarding plane that we're defining here, nothing fancy. The only piece of fanciness here is that we're actually dealing with parsing all the way to TCP, and we are calculating checksum. So that's all that the skeleton is doing in the beginning. And for our control flow, we just apply this forward table, nothing fancy, nothing being done on egress other than outputting the packet. Okay, so importing this P4 file into the project is not enough to actually get it to build. We need to go and configure the build settings to tell the tool that our main file that we want to compile, sorry, main P4 source file here, is the one that we just added. So that's just telling the compiler where to start working. If you want to save yourself a little bit of build time, you can reduce the number of worker MEs too. It's not in the instructions, but that's something you can do as well. Then we also want to tell the tooling, when you start up, sorry, there's a question there, yes? Okay. When you start up Programmer Studio, it assumes that you're going to, by default, do things in the simulator, and we want to now configure it to do the debugging on hardware. So that's an important step. If you don't do this step, you're not going to be debugging on hardware, you're going to be debugging in simulator. So please debug, select hardware. At this point, we can actually build our project and check that everything that we've done is correct, that everything builds all right. So if we've included the main file correctly, it's a question. Sorry? Slow down. Okay. We haven't started yet. Okay, I'm going to give you guys some time to catch up here. Okay, so at this point, you should be getting near to the stage where you've built the firmware for the NIC. Now we'd like to configure it with some rules. So we have a rules editor in the IDE. Typically, these rules would be provided by some runtime controller that is external to the IDE. So this rules editor in the IDE is just a convenient way at development time to define rules in these tables that will be installed when the card is started up. And those rules can also be modified at runtime using the IDE. So you can change the rules while the code is running, and we'll actually see an example of that if we get to the other lab. So now I'm going to do something different. I'm going to say file new, and I'm going to create a P4 user config file. So this user config file actually behind the scenes is a piece of JSON formatted data that defines, amongst other things, the rules that are going to go in the table. We should give this thing a name, so I'm just going to call mine config. You can pick any name, doesn't matter. And I'm going to check this box because I'm lazy and I don't want to go and insert it manually. So this is going to automatically insert the file into the project. But that's not enough, because we also need to tell it that it's our main one in the build settings. So we configure the main, user config file, we select it from the list, and then we're done. Yep. Oh, sure. So for those who haven't been following along exactly, we're now at just after this stage. We've, where's this numbered in the document? So we're at point 11 in the document. Okay. Where's the config file? So you create a file new. So you have to create it. So if you look at the previous step. Okay, so if you go back, step 10, file new, create a config file. Okay, I'm ahead of that now. And I think I did an earlier step too, a later step as well. I should actually follow along. Okay, so now what we'd like to do is we'd like to create a rule to match. Now if I just go back to my original diagram here, I'd like to create a rule that says if the packet comes in on the physical port, if it comes in on port P0, I'd like to forward it to virtual port 0. So the numbering scheme here is this says it's virtual port 0 on PCIe interface 0 of the card. The card has up to 4 PCIe interfaces. So I'm going to create a rule that forwards packets from P0 to V0. And because we're implementing a virtual network forwarding function here, I'm also going to create a rule that forwards packets from V1 to P0. So there's going to be some virtual network function that listens on both of these. And we're only dealing with the one direction here, so I'm only going to create the in P0, out V0, and then in V1, out P0 rules in the forwarding table. So that's what I'm going to do here. So for the forwarding table, I'm going to add a rule. I'm going to call this one physical to V0. And this is going to be an exact match, and it's an exact match here because my P4 code that defined the table, so from the data plane side of things, said that this thing is an exact match. So that's how it knows that I'm looking for an exact match here. So I'm going to match on P0, physical port 0. Similarly, the actions that are available for me to choose here are based on the table definition in the code. So because my table defined do forward as the only legal action, in my table editor, the only legal action I can select is do forward. And again, in turn, because do forward, the action definition in the code says it expects something called espec. I have a parameter here called espec into which I'm going to put the virtual port it must go on when it forwards. So that's v0.0. So this is now creating the one direction of flow. I'm going to create a second rule to go the other way. So from v1 to physical. Now, just going to say it again to be clear. I'm sending from P0 to virtual function 0, and from virtual function 1 back to P0. So unless there's something running, some VNF running on the host that forwards those packets, nothing's going to happen. So now I'm going to match v0.1, and I'm going to forward that to the physical port. And at this point, you can save the config file by pushing Control S. So at this point, we're at step 13. Now, if you were paying attention earlier, you'll see I had already done step 14. I got ahead of myself. So I'll just show you that again. So in the build settings, now that we've defined this config file, you need to specify that as the main user configuration file for the project. So at this point, if you want to actually run the thing, you can, actually let's not do that. You could run the thing and you would have to provide something on the host that forwards between those two virtual functions. And that's not done yet, so I'm not going to run the thing yet. But you could run the project now. I'm going to, in the interest of time, just start defining the new stuff. So if you look at this workbook, the convention that we've done here is the new code that you need to add is in bold type. And the context where you would like to add it, most of the time it doesn't matter too much, but some people want to know where to do things, is in normal type. So you don't need to cut and paste everything, you just need to cut and paste the bold stuff. So for this lab, what we're trying to do is we're trying to measure the latency of the virtual network function running on the host. And we try and do that measurement in the NIC. So we need to add a header to the packet to store somewhere in the header a timestamp before the packet is sent to the VNF. And then when the packet comes back down from the VNF into the NIC, we're going to extract that timestamp, compare it with a new timestamp, and that's the latency, the amount of time that was spent functioning in the VNF. So for that purpose, we're going to abuse TCP options. So we're going to insert a TCP option, and this is actually a legal option type. There is a timestamp option in an existing TCP extension to do timestamps, but we're going to abuse it, not use it the way it's intended to be used. But it has a layout that looks like this. So it has a 32-bit timestamp, and it's got a 32-bit echo response time that we're not going to put in. And if you know anything about TCP options, you need to define the type of option it is, as well as the length of the TCP option data. So this is what a TCP option header would look like. So by including this header definition in our P4, I'm not sure why I'm not being able to, oh, there we go. We just, okay, I'm going to open this in another web browser because it's not letting me paste it. That's better. Gosh, I'm not winning with this cut and paste job. Good, that'll slow me down, so it'll make it easier for you to keep up. And then we also need to instantiate this new header. So this is all just normal P4. Okay, there's an instance of the header. And by doing this, now we've done something very cool, right? We've taught P4 what a new type of header looks like. So this is where the protocol independence comes from. Just with a bit of code and a declarative description of the header you want to parse, you can teach the NIC about new protocols. So we also need to teach it where this header can happen, and for that purpose we need to make changes to the parser. So we need to explain to the parser, we have to teach it that something called a Tcp option exists. And we have to tell it where in the parse tree this can happen. So where we were parsing TCP, and just to explain what's happening here, so this was the special magic that we did to save the length for the TCP header, the TCP checksum calculation. The TCP data length is the number of 32-bit words in the TCP header, and now we're multiplying that by 4 to get it to bytes. So we're doing a calculation on that. But the point is here, instead of just returning the parsed representation at the point where we've finished parsing TCP, we're going to go further. We're going to look, are there some TCP options at this point? And the way we do that is with a selection at the current cursor position of parsing. Is anybody else also battling with cut and paste? I'm having a really hard time with it. Yeah, when I tried this yesterday, it worked fine, so I don't know. Okay. So when I ran through the stuff in the dry run on my laptop, it didn't happen previously. But anyway, there we are. It means we edit the source, it's fine. We are developers after all. So to explain what I've done here, we're now trying to figure out if we have that TCP option in the packet here in the parser. So if the option's not there, we can't parse it. So this select is concatenating whatever the previous thing that we parsed at this point. The previous header, that's the latest, had a field called data offset. That's in the TCP header that we've just parsed because we extracted TCP, right? We could equivalently have said TCP.data offset here, but that's not here nor there. It's just one legal way of doing it. And then we're concatenating some look ahead. So we're peeking at the next 8 bits of packet data, and that happens to be where the TCP option would be, the option kind field would be. So if the option kind is 8, and we're just abusing the data length and the fact that a TCP header with just one option. So this code is fragile. That's what I want you to understand. This is not how you would do it in production, right? So we're just matching. If we see a packet that had a TCP data length of 8, which just happens to be the length of the TCP header with our option added, and if the kind of the option was 8, which just happens to be the TCP timestamp option, then we're going to go ahead and parse this new thing that we've taught the parser how to do. Now we said we want to add a timestamp in this TCP option, but where do we get a timestamp in P4? So P4 hasn't really defined how you get timestamps from the hardware. So one of the things we've done in our implementation, and this is something that the specification allows you to do, is you can define intrinsic metadata that the pipeline knows about. So if you define the thing with the right structure and the right names, the NIC framework is going to automatically populate this metadata with a timestamp for you. So we're going to create a new metadata type that's going to contain our timestamp. And then we need to instantiate it. So by instantiating this intrinsic metadata that we've defined and calling it intrinsic metadata, our platform knows to populate this with the timestamp for you. So what do we have so far? For those that are following, we are now at step 21 of the instructions. So at this point, we've got a parser that understands how to deal with this new TCP option, and we've got a timestamp. Now we need something to take that timestamp and put it into the option on certain packets that are going to this VNF. So for that purpose, we're going to define an action that does just that. We're going to do this in the egress pipeline, so I'm just going to put it here for P4 doesn't really care where you define it in the code. This is just pure, organization of code so you can find it and maintain it. So we're going to define an action called do insert timestamp option, TSOpt. And the first thing we need to do is actually go and add a header. And in P4, what that does is it adds you a header initialized to 0 for all fields. So we need to go and set the individual fields of this new TCP option that we're adding to this packet. So we set the kind to 8. That's the timestamp option that we're abusing. Its length is 10, the way we're using it. We're not actually using this ECT field. So I'm just setting it to 0. We could just as well have left this out because the default is it would have been initialized to 0. And the TCP options need to be padded to the end of the last 32-bit word of the TCP header. So this is also, again, not a general solution. It's just relying on the fact that we've got exactly one TCP option that we're inserting, and it's exactly this TCP option, so this is the amount of zero padding we need. Don't go and do this in production. And very importantly, this is where the magic is happening. So here, we are copying this timestamp from the intrinsic metadata, and we're putting it into the TCP option header. Now we need to do another thing. We need to go and update other headers that are affected by this change. So we've inserted bytes into the packet. That means the size of the TCP header has changed, and the offset of the TCP payload has changed. And the IPv4 packet length has changed. So we're going to add the size of the option to all of these. So this is the data offset again in the way TCP is defined is a number of words, number 32-bit words, and in these headers it's a number of bytes. So that's why it's 3 here and 12 and 12. And that's the length of this TS option header that we've defined. So you'll see it's a 12-byte header if you go and add these fields up. So now we have an action defined for populating this header. We actually have to define when is this thing going to happen. And the only thing that can kick off actions in P4 1.0 is to have it be in response to matching something in a match action table. Yes, there's a question. So the question is if we can just go and explore the select statement in the TCP header. Is that what you want to look at? So yeah, in the past TCP, what's the question about that?
You are reading only 8 bits with the current offset.
That's right.
But you are comparing with the 16 bits.
Well, so there's two fields specified in this select here. There's a comma here, and it's the concatenation of these two fields. Yes. So this is something that P4 allows you to do, is you can concatenate more than one field into the select. So we're concatenating the data offset from the previously passed header. That's what latest is. So the previously passed header was the TCP header that we extracted.
But what does that data offset represent in this context?
What is the?
What is the data offset represents in this context?
Okay, so the data offset here is defined in the TCP header. So the TCP header, if you look at what a TCP header looks like, there you go, has a field called data offset. Yes. Now for a packet that contains our TS op that we've added, the data offset won't be the value of it'll be bigger than the offset would have been if those option headers haven't been there, because the reason that data offset is in the header is to allow you to skip over the options.
The data offset is 8 because we added 3 more.
Yes, right. So TCP, yes, exactly that. Is 5. Yes, it's 5 words, yes. Yeah. Yes, and now we're adding. So it would be enough to, in our case here, to just look at the length. That would have been enough to differentiate between the two cases here. This is still hacky what I've done here, but it's less hacky than just looking at the length. We're looking at the length and what type of option. No, because you can't just compare current offset to that might be packet payload. So, yes. So you can't. So you need to at least look at the data offset. Yes, and I mean we're making this code hacky and simple for example purposes, but we don't want to abuse it completely, and so that's why we concatenated the two fields like that. Yeah. Okay, so now we're going to create an egress table. And then based on the egress port, we're going to either apply this timestamp option or not. I'm going to go claim these cut and paste issues are there to force you to read the code so that you can learn more from this exercise. I think that's what I'm going to go say. Yeah, the reason I'm not doing that is if I make a mistake, it's going to take me long to find out what I did. This way I'm less error prone, right? Sure. As you see, I've now cut and pasted over a page boundary, so I've got a bunch of nonsense here that we don't want. Page number. Okay, so now we've defined a table. Yes, another question? So we're not explicitly setting that timestamp. That's the question. Where are we updating the global timestamp? So what I was trying to explain was that the P4 specification allows a implementer or a target platform to define intrinsic metadata that it just exists. So what our platform does is if you define metadata with that type and that name, the NIC software will actually insert the timestamp for you there. It's just available. It's assumed that the hardware provides it. Okay, the format of the standard metadata is defined. This is other intrinsic metadata. So the standard metadata is also intrinsic, but that's already defined in the spec what it looks like. So we're adding other metadata beyond what's in the standard metadata. Yes, are we good for time? Yeah, that was what we kind of. Yeah, should be good. And we also need to, in our egress control flow, define when we are going to apply this table. So what this is doing is we're not even going to bother applying this insert TS opt table unless we're dealing with a TCP packet. We shouldn't do that, right? Because if we execute this action on something that's not a TCP packet, we're going to corrupt whatever data is there. It's not going to have the right semantics if we did that. So we need to be sure we're dealing with a valid TCP packet, because the table itself, the selector in the table is just an ingress port. So we could get other packets on that port. We only want to apply this table if it was TCP. And we also don't want to add the timestamp twice. So if we found a packet that had the timestamp already, we don't want to add another timestamp. So that's what's happening here. We create an expression that says if it's TCP and it doesn't already have the timestamp, then go figure out if we need to insert this timestamp option by querying this table. And from a source point of view, I think we're done. We just need to configure that table. So now we're at step 25 of the instructions. If we go back to our rules file, now you'll see we don't have the table we want yet, because that table, insert TS opt table that we've defined is in our source code, but we haven't built our source code yet, so it doesn't actually exist. Okay, so this question was already Asked and answered. Right, so the timestamp, the P4 specification allows targets to define intrinsic metadata. This is metadata that's provided by the hardware that's just available. So in our implementation, if you define something with that name and that type, the platform is automatically going to insert the timestamp into that field whenever a packet ingresses. Okay. I will not answer it a third time. It's getting from the next. Yes. It's a next timestamp, yes.
Now the next timestamp and TSC are not necessarily.
No, they're not necessarily. So there would have to be some external mechanism to synchronize them. Again, you defining the application, you would define what that mechanism is. So maybe you would send a synchronization packet from the NFP periodically when you would do a certain timestamp. There's various ways to do it, or you have something from the host that you somehow with you'd have to do some synchro because that's not something exposed. Sorry? Okay. But this is also not a valid, we're using that Tcp option. Yes. Okay, so we need to build our project again because that table type that we, that insert TS option table only exists in the source code that we haven't built yet. So the only way that the tools node exists is if we've built it. Okay, and like magic now the insert TS op table exists, and we can now add a rule. So this is now at step 25 of the instructions. So I've added a rule here, and we're only going to do this in the if we're egressing to the VF attached to our virtual network function. So I'm going to give this thing a name, so insert for VF0 or something. Well, it doesn't matter, I think, what did I call it here? Insert TSV or whatever, it doesn't matter. The name is irrelevant. So when we want to egress to VF0, then insert the timestamp option. And note, in the code, this action doesn't accept any parameters. So the table doesn't allow you to define any parameters. So it's again something that's defined by the data path structure, what parameters you can pass to an action. Is there a question? Okay, so now we have code that should insert timestamps into packets. This is awesome. Shall we see if we can run it on hardware? So, can I ask everybody to stop for a second and pay attention? This is very important, this step, okay? So, this is where the second card that you got that has the details about your hardware. When you get to the point where you want to actually deploy this on hardware, you need to tell it where is the hardware. So, under hardware options, that's where you fill these details in. Okay, so each of you has got unique details for a unique piece of hardware, and that's what you fill in on this page here. It's also the server that you're going to SSH into with PuTTY to TCP dump things on those VFs and attach them together with a mock virtual network function. Okay, thank you. I'm going to fill my details in here. Do not copy my details, okay? Because you're going to interfere with what I'm doing if you did that. So I'm going to select to connect via the Ethernet network. And my server address happens to be this, which you should not see or copy or do anything with. And note, you do need to set these debug port and runtime server port numbers because we actually have more than one of these physical NICs per server. And you need to tell the tools which one of the NICs to connect to. When you secure shell in, you put into a network namespace that only sees that NIC, but this tool is not network namespace aware in terms of Linux namespaces. So you'll possibly specify a different NFP device number. You'll possibly supply a different debug server port and runtime server port. Good. Having defined the hardware details, I should be able to just start debugging. So you can either select from the debug menu or you can push this little bug here on the toolbar. So the bug inserts the bugs that you have to debug. That's why there's a bug there. Then you can SSH into the same server that has the hardware in. And as username, use the UID on the card. So there's 2 user IDs per server. Use the appropriate one, otherwise you'll interfere with one of your neighbors. So you'll see it drops you into a root shell when you log in as that user. And the only interface that exists at this time is the loopback device and this P1 interface, which is the standard NIC that's also installed in that server. The standard NIC being looped back with a piece of cable. Do you have a question? Yes? Can one of the assistants please assist in front here? Somebody's got an issue that Bidad's on his way. So this is the NIC that we're going to, yes. Hello? Is that a question? Okay. So this is the NIC we're going to play traffic on, and we expect it to arrive on the smart NIC because there's a loopback cable. Right. Now we can stay loading microcode. Yes, is there a question? Yeah. Yes. Yes, sure. So there was a question about where do the headers get added when you add a header, and the answer is that is determined by the parse tree as determined by your parser definition. So one of the things that's nice about our tooling as well is you can select these IR graphs from the view menu. And one of the things you get there is a visual representation of the parse graph. So you can see the way we defined our parser, we have an Ethernet header, and then we might parse an IPv4 header, then we might parse a TCP header, and then we might parse TCP options. So where the header gets added is determined by this parse graph as defined by your parser description or your definition of your parser. So if you go to View, IR Graphs, then you can get to see a picture of your parser. Good question. Thank you, Gobis, for bringing that up here. Okay, where am I? I've just started. So I've clicked Start now on my debugger. And because I've done that, you'll see now that the NIC software has started up, if I look at what interfaces are defined on my server, I have all these virtual interfaces defined now. There's a netdev for v00, a netdev for v01, a netdev for v02, and a netdev for v03. So these are the same virtual ports that I've defined in my application. Or rather, that's how this NIC is configured. And I can use them in my application. Same virtual ports I can use in my application. So I don't have a VNF to run here that's interesting. I'm just going to pretend to be a VNF. So I'm going to add V0 and V1 into the same Linux bridge. And by doing that, I've got a forwarding VNF. It's a mock forwarding. It's a very dumb one. It takes whatever it gets on the one and puts it on the other, but it's some forwarding VNF. Imagine it is there. All right, so there's a couple commands to do that are starting at step. Sorry, I'm getting ahead of myself again. Forgive me, I've done this demo so many times. All right, so what we're going to, before we even add the VNF, sorry, ignore me. Let's have a look what's happening if we dump the traffic on this V00. This is where we're forwarding packets that come from the physical interface. I'm going to open a second PuTTY terminal. So I'm going to duplicate my session so I can also have one to play back the packets. And on this terminal, I'm going to use the Tcp Replay command to insert a packet into this interface. And this is a normal TCP packet. And the interesting thing to note is these TCP packets now have this Tcp option inserted. So this is why we abuse that specific option, because TCP dump knows how to parse it. We could have defined our own, but then when you dump it in TCP dump, you wouldn't have seen it. And if I send another packet, you'll see it gets a different timestamp. So each of these packets that's going to this virtual function is getting a timestamp inserted. Now, because it's a valid TCP option, any forwarding VNF wouldn't be affected by that. It could just make the same forwarding decision it would always make, and it can ignore this timestamp because it knows how to skip over TCP options. Every compliant TCP stack must know how to do that. So you could still build a forwarding VNF and have this timestamp insertion being transparent to the VNF. It doesn't know that it doesn't have to deal with any special headers because it's a TCP option that's either there or not there. It's nice and transparent from the point of view of the VNF. We're also going to make it transparent just now from the point of view of the network by when the packets come back from the VNF and we extract the timestamp to do the calculation, we also remove the option again so that the packets that get forwarded look exactly like the packets that came in. So then it becomes fully transparent measuring of the VNF via in-band telemetry. Okay, so that's awesome. If we look in the counters tab, so while you're debugging, there's also a P4 inspectors. So if you go View, Debug Windows, P4 inspectors, there's all sorts of interesting counters that are captured under the counters tab. And some of the ones that we are interested in here, I note you need to refresh this. It doesn't automatically refresh. You can see the 3 packets that I've sent. That's what the RX counter is counting, is how many came in on any interface on the NIC. On any physical interface, and then the RX NFD are the packets that arrived from virtual interfaces. So NFD is our Netronome flow driver that runs on the host. So those are packets that are received via PCIe. I haven't sent any packets on PCIe, so there's none received. And these flow cache hit and miss are implementation-specific things. It's how we accelerate P4. We also cache flows in that flow tracker that you saw in the slides that Johan showed you earlier. So that's what's happening here. The first packet missed the flow cache. The subsequent 2 packets hit the flow cache and were accelerated. Even beyond, we run the PFE in hardware, and then we do some caching, additional caching in the hardware as well. So that's what we're seeing on the counters here. So also interesting is because of the way we define the checksum handling, if we feed an invalid TCP packet in, what is the name of it? What do we call it? TCP_invalid. So this is a PCAP file containing a TCP packet with an invalid checksum. And note, in our TCP dump now, if I send in this packet with an invalid checksum, nothing arrives, right? That packet, when we consult the counters, is dropped. Because our P4 logic that we implemented said we're only going to forward packets, that we're only going to apply that forwarding table if the checksums are valid. Well, in fact, it's more fundamental than that, because if you define the checksum, and if you have a verify in your calculated field, it will automatically drop packets that fail to verify the checksum. That's how P4 works. So it's because of the way we define this that we drop invalid packets in this implementation. Had you not done this, you would have seen the invalid packets on the host. Okay, now we get to actually defining the VNF. We're almost done. I need another 10 minutes or so to finish. So now, let's stop the debugger. So you want to exit, yes, and then no to stop the MEs. Now we want to quickly add code to extract that timestamp on the way out. So, this is another thing unique to our implementation, right? Again, the P4 specification allows hardware to provide intrinsic primitive actions that are intrinsic to the hardware platform you're running on. And those are just a handle in P4 that you can use to call that action. So it's just declaring the interface of this action. Now, in our implementation, because we have a software pipeline, when you do this, when you say you have a primitive action called TSOpt statistics, we allow you to go and write some C code with that interface. And that C code, sorry, this is still P4 to call it. I'm getting ahead of myself again, so let me just show you what, okay, let me first add this, and then we actually need to have, you still have to have a P4 action to call this primitive action, and we still have to put it in a table and match it and do all the usual things. And I want to just, that's not interesting. This is just duplicate of what we've done already, so let me rush through that because I want to get to the interesting, the meat of it. So here's the removal of the header on the way back in. I said we're going to remove it so that it's transparent. And if we remove it, we need to update all the length fields again. So we must subtract from, like we added when we added the header, we need to subtract when we remove the header from all of these TCP and IP fields that exist. So that's all still defined in P4. But the special magic to actually do something interesting with this timestamp, to store it in a log and calculate average latencies and minimum and maximum latencies, all of that logic is happening in a piece of C code. And we call that by just declaring that it exists and calling that primitive action that we've defined. And once we've done that, we can now create the table that says when we're going to process these things. So there's some table to process these things. And it has an action of do process. And we need to declare in our control flow where this table is invoked. So in ingress, if we get a packet that has a TCP timestamp option, we'll process the timestamp option. It's very simple, right? And if it isn't there, we don't process it. So we can put that in our ingress pipeline. in our ingress control flow. Before we forward the packet, let's see if we have to deal with timestamps. So that's what we're doing here. So if the header that contains the TCP timestamp option is valid, i.e. it exists in P4 parlance, then process that timestamp option and apply forward action then after that as we did before. Okay, so from a P4 pipeline, we've now defined when this action is going to happen. Now we can insert that C code into our project. So we insert P4 sandbox C. So from the project menu, insert P4 sandbox C. And again, we navigate. We've already pre-written this C code for you, so you can, from the files you downloaded at the beginning, P4 lab int, there's a plugin that we're going to load into our project. And again, we need to, like we did for the other things, say this is the main C file for our project. So in our build settings, select this one we've inserted as the main C file. And once you've done that, and saved and build, we should have our plugin inserted in our project. So let's have a look at it quickly while it's building. So this is normal C, right? This is exactly like C, except that we have a few special register types. We're not going to get into too much detail on that today. But essentially, there's a interface that's generated from your P4 code that understands the headers that your P4 code is defined. So you can, if you define an IPv4 header, there's going to be a PIF plugin C function that allows you to access that IPv4 header. And here we define that standard metadata, we define this intrinsic metadata with the timestamp. And again, we can access that to go get a timestamp. So all the, what's the word I'm looking for? All the definitions that we've created in the P4 are now accessible from the C through that API that's been generated from the code. And then we go and figure out, is the latency more than the max that we recorded? Is it less than? It's very, very straightforward C to calculate an average and a min and a max. This is like computer science 101. And at the end of a plugin C function, you must give a forwarding decision because you can also drop packets in this C function. So this just says continue forwarding it according to the control flow at the point that this action was called. So very basic C. We've built it. Let's run it again. Okay, I need 5 more minutes to finish, so almost lunch. So at this point, we're at step 13 of the second part of the lab workbook. And now we're finally getting to defining that VNF that I got ahead of myself with earlier. So on the host, I'm going to add a bridge that's going to represent our VNF. Add bridge. And I'm going to add to that bridge, so I need to now wait until the code is loaded because those VNFs, those virtual functions don't exist until the code is finished loading. So I need to add those virtual functions to the bridge. So now I just need to wait for the code to finish loading to do that. Maybe 7 minutes from when I said 5 minutes. So now it's busy configuring the MAC of the SmartNIC. Our MAC is also configurable, can change depending on the software. Does various steps. Are there any questions that I can answer at this time? We're not going to get to the other lab, So we're just going to finish up with this lab and then we're going to have lunch. So these VMs, we'll leave them running after this evening and probably for, I don't know how much longer, but a couple of days probably. So you're welcome to continue with the other lab in your own time. Okay, so now that the software is loaded, again, these virtual functions exist on the host. So now we can add those to the bridge that we just created. Add interfaces to the bridge, v0.0 and v0.1. Sorry, not bf, br. Okay, so if I do this, now you can see that we've created a Linux bridge and we've slaved these two interfaces. So what this does is anything coming on this one goes out there. It's a standard L2 bridge. And let's just bring our bridge up. Now we're done. So let's dump now. Now what I'm going to do is I'm going to dump traffic on the other standard NIC that's in the server. So I'm going to look at the traffic ingressing and egressing from the physical port. Remember to actually start the MEs. That's important when we're running in the debugger. And now I'm going to play that TCP packet in again. TCP Replay, root TCP PCAP. And what we expect to see is we expect to see the packet twice. We see the packet going in into the P0 device, and we see it coming out again. And why? Oh, and I was expecting to see the packet not have the timestamp in when it came out, but because I forgot to add, so this is a good time to show you runtime configuration of rules. I forgot to actually add the rule to process the timestamp action, the timestamp header in the table. So let's call this process timestamp. There is only one action possible here, so it's the default action, and it's to process the timestamp. So when I save this, it asks me, do I want to reload the rules? And I say yes. So now at runtime, we are reconfiguring the rules installed in the NFP from the control plane. So you can see this rules editor tool in the IDE as a model for the control plane. So now if I do the same exercise again, and let me just make a little bit of space here, without restarting the code, without reloading, rebuilding, anything, when I play it in now, I get exactly the same packet in and out. And crucially, I have captured some statistics about this packet that processed as it went through. So there's a runtime API for accessing the stuff written by that C function. And we've got a minimum latency, a maximum latency, and an average latency of the one packet that we saw, so it's all the same. If we send a few more packets, you know, we might get slightly different variations on this result, but they're all in the same kind of order of magnitude of time, 0.1 milliseconds. And then the last step that we're going to do is we're actually going to use NetM to impair this bridge. So we're going to make the VNF slower. Our model of the VNF we're going to make slower. So I can do that by adding to the egress device a delay of 100 milliseconds, for example. And now you'll see if I carry on playing packets in, so let's just watch these statistics here. Watch minus n. N1 minus d root stats. So now we're just watching for statistics updates. If I play a packet in now, we'll see that all of a sudden the packets are taking 100 milliseconds to process through the VNF. So we are live measuring the performance of that VNF from the control plane, and it's transparent to the VNF and it's transparent to the network. And that's it.